next week.
That's next week too? All right, so we can ignore everything on Blackboard because I forgot to put those two details in there. I've got to slip things. We're not going to get as far as I hope we would, okay? So anyway, make sure you come prepared. For your, notice this is incomplete, it says oral report, but you're also going to have to submit a one-page proposal that looks like this, and you submit that through Blackboard. So as soon as I get back to the office, I will fix Blackboard, and there obviously won't be a homework due on Thursday. This will be due Thursday. Okay, so I've got to fix everything. everything is wrong right now because I forgot to slip this in, and then of course I need to put the midterm on the schedule. Make sure we've got that done. And usually I do a take-home midterm. Does that give you one, Brian? No, that's not good. I will do that too. So I'll actually probably try and get both those up today. If not, certainly by, well, I'll certainly fix the lightning round thing because we've got to submit that tomorrow. And so make sure you bring out along at least one of these printed out for me. I've got to have something to hold in my hand, okay? So bring at least one copy of this. And whatever you do. And this is the format I like. Okay, the next thing I want to do is oops. I want to talk about homework for a minute. So, obviously I don't have my name, date, and CMSS up in the corner like I'm supposed to. But this is kind of the way I want you to do the homework. You know, you can repeat the question. You can kind of show the code, and then, you know, show me the answer. And for that homework, you really don't even need any, text. Okay, so that was the one that was due last Thursday. And the way in which most of you we still had at least 3 or so who got this wrong. Was it this one? Yeah, and it's because you didn't do this part correctly. And you had to start with the data set. This was the key thing. You had to start with this per core data set. And if you do, that data set, once we get here, you should have 75 lines. A lot of you are coming up with the wrong number of lines still. And then on the one that was due today, that's 5. Which is 6, right? Again, you had to use the correct data set. And again, 2 or 3 did not use the correct data set. This data set that I called composite should have 75 rows. You see, n is 75. If you don't start out with n is 75, you can't get the right answer. It's just that simple. So where does the 75 come from? Well, it comes from the number of stations multiplied by the number of dates multiplied by the number of replicates. So I've told you, I've done this a whole bunch of times, and we'll do it again today. The first thing you do is you map and diagram your experiment and do the friggin' math. And then check in your log to make sure the numbers match up. Understand how many rows should be in your data set, and then look at the log and make sure the data set actually has that number of rows. It prints it out. You know, every time you do anytime you do any kind of proc or data step, one of the notes will say how many rows and how many variables. Look at that. If it doesn't look right, you know you're going down the wrong road. And so for this one, a lot of you had 775, which was the original data set. It wasn't a composite data set. And it should have been obvious to you, how do I get 6 dates, 4 sites, and 3 reps and get a number? How do you multiply those 3 numbers and get a number like 7875? You can't. It's at least an order of magnitude too big. So if you follow the process I keep showing you, right? Map it out, build your model. A lot of these things should be intuitive. And the point is, I'm showing you a way to check your work as you go along. So you really need to do that. So basically, this is the answer. And frankly, the only reason I asked you this question is so that I can make sure you have the right data set. So I'm kind of lazy and always try and figure out easy ways to grade homework. And if I ask you to calculate the overall mean, and if that number is correct, then you have to have used the right data set. It's just that simple. So the real question was the second one. And I expect a sentence that looks like this, guys. A lot of you are really lazy. You know, I don't really care what, but they print out 4 different tests for normality. I don't really care which one you use or if you want to average the numbers or what. I'll be honest with you. I have researched this a whole bunch of times, and what statisticians really say about these normality tests is they're probably a lot of hooey. In fact, I once had a course from a guy who got his PhD from Fran Wilcoxon. If you heard of the Wilcoxon rank sum sign test, she was a very famous statistician. And he told me that she once said in one of her lectures, using these normality tests like Shapiro-Wilks and all the others to test to see if a data set is okay for ANOVA is like using a rowboat to see if the ocean is okay for the Queen Mary. And the point here is that ANOVA is so robust, it really doesn't matter if your data is normal or not. You're going to get the right answer. I believe the right number is 99,999 times out of 1. So you'll only get the wrong answer 1 in 10,000 times if you have a non-normal distribution. And there's a ton of research showing this. All of this was done in the 70s and early 80s, by the way. This is not news, okay? So when I was in your class, in your position in the early 80s, non-parametric statistics was all the rage. Because everyone was absolutely convinced that a non-normally distributed residual was this great, horrible thing. Well, statisticians did a lot of research, primarily through simulation, and discovered that, oh my God, even if you have a uniform distribution, what's a uniform distribution? It's a straight line, right? So a normal distribution looks like this. And the significance of the normal distribution is that 68% of the samples are within 1 plus or minus 1 standard deviation. And the mean is at the 50th percentile. Now, the way about 90% of the ecological data looks, it looks something like this. Meaning that the mean is somewhere to the right. This is skewed to the left. So so here, the mode and the mean are different. Here the mode and the mean are the same, okay? So this is pretty common in our world. So what's a uniform distribution? It's a straight line. It means every value occurs only one time. So the mean in the mode is like infinite. Well, the mode is, there is no mode, because everything has there's nothing that occurs the most times, because everything occurs only once. The mean, of course, would be the middle. And so what the research did is they compared ANOVA with this kind of distribution compared to that kind of distribution. And like I said, they found that when you run these sort of experiments, you get the right answer with ANOVA 9,999 times. That was the magic number. 1 in 10,000 times you make a mistake. So from that, everyone concluded that, geez, maybe this assumption orthogonality is not so important after all. ANOVA still works whether it's there or not. Okay, so that's what professional statisticians know and do. And as I said, and that's one reason why SAS has got these 4 different ways to do it, because there's no consensus that A, it's important, or B, there's a right way to do it. There is a consensus among the statisticians I've talked to that all of those tests for normality are weak at best, as opposed to ANOVA, which is very robust. So what's the punchline? And if all of that is true, why do we bother spending so much time on it? Well, the answer is, when you leave this room, you'll probably run into the majority of people who completely disagree with me. So even though I think I'm right, I need to prepare you to deal with the people who think I'm wrong. So I try and give you a complete story without bias. And I truly mean that, it's without bias. So I teach you how to look at the residuals. And as we get into the interaction term stuff, it'll really make sense why it actually matters. The other thing I've been trying to show you, and hopefully you notice this yourself, is that when you look at the p-values for the transformed and untransformed values, they're not all that different in the ANOVA tests. You know, so what's all the fuss about? Well, the fuss comes primarily from people who learn statistics from biologists like me, who kind of buy into this whole normality stuff. Anyway, the main point here is when you do your homework, write complete sentences. Too many of you are not actually not actually answering the question. So make sure you at least write a complete sentence, and then you can show all the code below. And for this one, I think everyone got this one right. Maybe not. I can't remember. The key was we had to create a variable that made the 6 sampling periods all one date. Yeah, what's up?
Why did you include rituals as well?
Because I wanted to.
Would we get it wrong if we didn't?
No, I didn't ask you to do that. I actually meant you to do that, and I'll tell you why I wanted you to do that. Well, because of the answers. I just screwed up when I was typing the question. I wanted you to have an answer where one was correct and one was wrong. So it turns out, whether you transform or not, you still don't, they're still both, according to the test, not normal. You fail to reject on all hypotheses that they're the same, okay? But if you notice with diversity, they're actually both normal with diversity. It looks like I don't have the period in the right spot, do I? Forgot the period here, okay? So, it's okay. I wanted to show you one where it meets the test and one where it doesn't. And I guess I just forgot. Sometimes when you log transform, it does. In this particular example, it was the diversity values were fine, richness values, but the abundance values were not. And I just forgot to ask you to do that. But you just heard it, so don't worry about it. We'll get back to it in another homework assignment later, particularly when we start doing multiple comparison tests. All right, and so then the other thing I did is, so I included this for one reason, to show you that there were 6 sampling periods and 1, 2, 3, 4 dates. I'm going to have to check this data set. What's 6 times 4?
24.
24. What's 24 times 3? 72.
There was a date in April.
What does that say?
That had an extra something.
75. There's something wrong with this data set. I'm going to have to look at that. I'll get back to you on Thursday.
It wasn't equal across.
Yeah.
There's something wrong with this data set.
In April, there's an extra, there's extra samplings of that.
There's an extra sample in April? How about that? I'll have to fix the homework data set because the numbers are supposed to add up, right? So you see how, you see the importance? Actually, that was a great teaching moment. You see the importance of a silly little summary like this? You find out, if you just do a little bit of quick multiplication, you should figure out what's going on. And so anyway, Procunivariate prints out these 4 tests. And, they always come out a little different. But as I said, a lot of statisticians believe that these tests are actually very, very weak and don't tell you much anyway. So, to be honest with you, most of the time what I do is, I still always look at the residuals, but I primarily just look at pictures like this, and then the probability plot, to determine, and I do it only to try and figure out which transformation gives me the closest results to normal as I can. And frankly, I don't do it because I don't believe the results. I do it for the reviewers. Because if you don't discuss these issues, reviewers go nuts. And long ago, I gave up trying to convince everyone else in the world you're worrying about nothing. So I just give them what they want. That's what we call practicality. All right, so do the homework correctly. Make sure you follow this format precisely. Notice we have our name, purpose, date. Obviously, this is from a few years ago. I still have 2013 there. Probably my first draft. I want a title and purpose. I want you to describe the data source. I want you to describe the study design. I want you to tell me your analysis plan. Notice that the analysis plan is essentially, give me the model. And I kind of leave a few blanks here. Notice an important part of data source is the specific citation. Now, if you're not using published data, it doesn't matter. Just, give me something that tells me where did it come from? Sources, where does it come from? All right, so all that's due on Thursday. All right, let's at least get started on what I really wanted to talk about today. This is another one I have a PowerPoint for. So, what did I do? I hate this thing. What is this crap? Oh, wow. This looks completely different on my computer screen.
Can you see
Do you
your
have it in
notes?
presenter mode, so you see
I
the
guess
next
so.
slide?
Yes. Because what I see is not what you see. That's okay. I had upgraded Windows. I didn't realize it was so different. Anyway, so what we're going to talk about today is multiple comparisons. Why are we talking about multiple comparisons? Well, we've talked about station differences and date differences, but sometimes we may want to know which date or which station is different from the others, right? And so that is the multiple comparison and problem. However, it turns out there's this nasty detail. So when we do ANOVA, and in all of the cases we've talked about so far, let's talk about the homework since I just had it up. Let's say we wanted to know if there are station differences. Well, the ANOVA p-value simply means, what's the null hypothesis for station? Does anybody know?
There is no difference between stations.
Yeah, there is no difference amongst any station. So it's actually, so the null hypothesis is A equals B equals C equals D. That's the null hypothesis, okay? Now, in fact, I can tell you in that particular design, what we were really wondering, it turns out A, B, C, and D in this experiment represents a gradient. And we actually expected things to continuously change from A to C. So not only did we expect differences, but it wouldn't give us heartburn if A and B were similar, and even C and D were similar, but we're hoping that at least the two major areas were different, the one that A and B is in, the one that C and D is in, okay? Does that make sense? So to tell you explicitly what that homework experiment is doing, we have, this is Nueces Bay, this is Corpus Christi Bay, and A is here, B is there, C is over here, and D is over there. And so the stations are aligned along a gradient of distance from the Nueces River, right? That's one part of the design. But also notice that two stations are in Nueces Bay and two stations are in Corpus Christi Bay. So, what we really wanted to know is Nueces Bay and Corpus Christi Bay different? So in estuary jargon, Nueces Bay we call a secondary bay because it's connected to a river, and Corpus Christi Bay is called a primary bay because it's connected to the Gulf of Mexico. And of course there's this little constriction with downtown Corpus Christi here and Portland over there, okay? And so that constriction kind of acts as a separating point. So if you think about it, this is a pretty uninteresting hypothesis. I mean, we expect it to be rejected and conclude that, yep, things are different, right? But now we want to know where are the differences. And in fact, as I said earlier, a priori, so there are two kind of hypotheses, right? Post hoc and a priori. A priori means this is what I started with. A priori is, well, now that we know there's differences, let's go snoop around and see if we can find them. So one is before the fact, one is after the fact. It's a statement of logic to say that a priori hypotheses are more powerful, more robust than post hoc hypotheses. Now, I'm using the words powerful and robust in the statistics jargon way, right? Power means ability to detect a difference. Robust means, do you believe that that's really different or not? And I think in the first lecture we talked about, did we talk about type 1, type 2 errors? Did you talk about that? Yeah. So you know all that stuff from Stat 101, okay? None of this is new. But my main point here is that I'm using the word power and robust in the statistical jargon sense, the statistical definition of those words. They're important. In fact, that all gets back to this nonsense, doesn't it? What I told you is even if the distribution is not normal, ANOVA is still robust. It means you don't need to worry about making mistakes. Robust means you don't need to worry about making mistakes. Or how robust something is how confident you can be in your end result. Power is different. Power is ability to detect change. So let's say A and B were different. How do you know you can detect the difference that actually exists? Well, that's what power is all about. And the answer is always, it depends on the number of replicants. You know, anybody watch the Academy Awards the other day? I did, I admit it. And I'm looking at the Academy Awards and I'm thinking, you know, that there must be a rule in Hollywood. You can't be too rich and you can't be too thin, right? If that's true, I think the analogous rule in statistics that you can never have too many replicants. But that would be that for statistics, that's what you say. You can never have too many n. So it turns out power is a function of n. And if you can't tell the difference between A and B, it's probably because we only have 3 replicates for each sample. And you know, in a perfect world, when I first started doing all this research here in Texas, which was in 1986 or so, I knew I should be starting all of my work using 5 replicates or 6 replicates as a minimum, but I just couldn't afford to do it. Because at some point, we've got to deal with the other parts of our design, the number of stations and the number of sampling dates. So in fact, this data set, the NC data set, so I call this the NC data set for the Nueces Corpus Christi. That was the very first data set I ever created in the Texas coast. And when I set that experiment up, I realized we wanted to try and sample at least, in an ideal world, we would have sampled monthly, but I couldn't afford it. We didn't have enough money to take that many boat trips. We didn't have enough money to analyze that many samples. So again, the total number of samples are the number of stations times your number of sampling trips times your number of replicates, right? So N is, And so at some point, you got to do a cost-benefit analysis in your brain and say, how much does it cost to add a station? How much does it cost to add a replicate? How much does it cost to add more sampling dates? And so ultimately, I can tell you by 1988, after I'd been living here for 2 years, I just kind of gave up and said, well, we're only going to sample 4 times a year now. And I'm going to try and limit myself to only 4 to 6 stations in any base system. And I'm just going to live with 3 replicates because I just can't afford to take any more. So that explains why I do quarterly sampling. It's just to save, it's just because that's all I can afford to do. We just simply don't have, and affordability is 2 things, right? It's not just money, but it's time. At some point, how much work can one individual actually get done in a year? And if you think about the context of a master's degree, how much time do you have to actually do lab and field work? If you have 12 months, that's a lot. Right? You start off your first semester and you're basically taking classes and you're trying to figure out what the hell to do. Then maybe you'll have your spring, summer, and fall to get all your research done. But you still need the last spring to actually write a thesis. So if you think about it, anyone who plans more than 9 to 12 months worth of field or lab work is never going to succeed. You will not succeed. It's just that simple.
I did that.
You learned that the hard way?
Yeah, I learned that hard way.
So, see, he didn't listen to me either.
Hey, you told me to go sample.
I told you to do that?
Well, you wanted me to do that. But I learned.
Suffering builds
I learned the hard
character. You need to learn how to stay up late at night and work Saturday to Sunday. All right, so anyway, the point is, when we set this up, our real goal was to find out, is there a gradient, meaning is there some kind of change going on from A and B? And also, is A and B different from C and D? Now, how the hell do you get that out of your p-value for stations? And the answer is, you can't. So what we have to do is what we call a post hoc analysis. So after the fact, we go in and we try and compare all the means. So your real problem is what we call the pairwise comparison problem. So we want to know if, like, you know, if we got A, B, C, D, right? Then we have B, C, D. We want to know if these 2 are different. Well, if this and this is 1. But let's do it the hard way. If I do it the hard way, it'll show you something important. A, B, C, D. So this is actually, A and A doesn't exist, B and B doesn't exist, C and C doesn't exist, and D and D doesn't exist. We should call them zeros, not ones, okay? But a comparison with A and B does, with A and C does, with A and D exists, with B and A, oh, that's the same as that. So we can get rid of it. B and C does, B and D does, C and A already exists, B and A already exists, B and C already exists. Oh, here's a new one, C and D. So in fact, and of course D and D doesn't exist. So the point is that we have all these pairwise comparisons, all right? And it's basically half of your sample chart, all right? Now the problem is, if we tried to test each one of those comparisons in like a t-testing situation, right? All t-tests, if we reject that type 1 equals 0.05, means you have a 5% chance of making a mistake. What happens when we look at the same data set over and over and over again? So in this case, we'd have to look at that same data set 1, 2, 3, 4, 5, 6 times. Well, if we run our 5% test 6 times, is the error rate still 5% for each test? No. This is something called the experiment-wise error rate. It turns out the correct error is, I'm not going to go through all that detail. The correct error can be found by this formula, which means it's actually somewhere, I can show you exactly what it is. So we just did, well, I wrote 3 and 8 here. So it's somewhere around 0.3. We know that one of those comparisons are going to be wrong at least 3 and 10 times. Well, that's getting pretty damn high chance of making a mistake now. So we can't do that. So the point is, a very long time ago, people realized that we have to control the experiment-wise error rate. And when we test these things, it's not a paired t-test situation where we're comparing the mean against a confidence interval for each cell. Because, and why is that a problem? Well, because the confidence intervals are based on the standard deviation of each cell. But in an ANOVA model, right, what's the ANOVA model? Y equals some overall sample mean plus alpha sub j plus b sub k plus alpha beta j sub k plus some overall experiment error rate, which is based on some number of replicates. Well, what is this? That's the true variance of the entire population. So what people figured out is, wait a minute, we can't compare two means based on the standard deviation of each cell because we're going to be making mistakes all the time. But we know we have estimated what the true population variance is, and that's this number. And where do I find this on the output table? Which row is that on the output table? Mean square error. Okay, mean square error equals variance. So MSE equals S squared. What's the difference between S squared and sigma? This is the true population variance. This is our estimate of the population variance. And that is calculated as something called MSE, or mean square error, in an ANOVA table. Okay, so we have ways to estimate population variance. So if we do all of our tests using only this value, then we are essentially controlling our experiment-wise error rate. And the true rejection rate for all your comparisons is always going to be 0.05. So that's why we do all of our testing for differences of means only in the context of an ANOVA test itself. And I'm not going to do that right now. Okay? So that's what's important. I don't want to get into all that stuff right now. I'm taking too long today. So, I don't know if anyone bothers ever looking at my lecture notes, but I go into a lot of the horrible, gory detail in lecture notes, and I also talk about all the different options. So as you might imagine, once this was discovered, which was something like, as I recall, I could be wrong about this, I think it was like, oh gosh, 1940s, 1950s, when people realized this was an issue. There was this huge hunt to build a whole bunch of different ways to do what we call multiple comparison tests, okay, which are all post hoc tests, meaning that we do our experiment, we estimate our error, and then we hunt around in this fashion by comparing all pairwise comparisons to see which ones are different. Now, it should be obvious to you that this is actually not the experiment I designed, right? The experiment I designed was really is A plus B equal to C plus D. That's the experiment I really designed. How the hell do I get that out of this? You can't. So, and it turns out this is actually a special case of what we call a general linear contrast. Why the word linear? Because this is just summing. We're going to just sum them all up. All right? So, most people in the world only do multiple comparison testing, and there must be 20 or 30 different multiple comparison tests out there. Some are terrible, some are okay. What really screws things up is when you don't have the exact same number of replicates in every cell. So that's the equal sample size problem. That leads to the homogeneity of the variance problem, which some people worry about a lot. And there are only two tests that handle this the best. One is the Tukey test, and one is this leg weight test. Okay. I think that T doesn't belong there. Okay? Tukey's is probably best when we do have homogeneity of variance and we do have equal sample sizes. What's nice about Tukey's is that it works really, really well no matter how big your experiment is, because it works directly off of the mean square error. There is an adjustment to Tukey's when you have unequal sample sizes. And it turns out what SAS implements it in a funny little way called a harmonic mean of n. So SAS literally takes the harmonic mean of n rather than going through the full adjustment thing. So it's kind of a, it's not as good as the original adjusted Tukey's was, but it's okay. Some research has shown that this is actually more powerful than Tukey's, meaning that it can find, if there's a difference, it'll find it. You don't have to worry about saying A and B are not different when they actually are. That's what power means, ability to detect change, right? But it really, really doesn't work at all when you have unbalanced designs, meaning some of those cells have just two replicates. Okay, that would be a big problem. So, a lot of people like this test. To be honest with you, I always use Tukey's and nothing else. That's my personal preference. Okay, and with that, we can find out if we can do this. And the way that gets, and I'll show you the implementation right now. Oh, good, I have it right here. So the implementation's a piece of cake. You have your, this is for a one-way design. You have your model statement, treatment A, and all you gotta do is invoke the mean statement. You put a slash there, the slash means, here comes my options. And you write, simply write Tukey, and I'll explain what the lines are in a minute. But instead of Tukey, there's about 30 different tests you can put in there. Let me see the next slide. So it's real simple. So there's a bazillion, there's not 30, I exaggerated. It looks like there's only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So SAS provides 14 different multiple comparison tests. It also provides two other important things. Three other important things. The lines option arranges the means from highest to lowest, and it underlines the ones that are not different, which is a typical way that we present this kind of data. So that's very convenient. The no sort option would not put them in order. I don't know why on earth you would not want them ordered. And then finally, for those who get real worried about whether or not all of those cells have the same exact standard deviation, there's also the homogeneous of the variance test, which is called HOV test. I never look at that. And then if this is a big problem, you can always add this, which will compensate for that. So you can run your ANOVA the first time with this. If you pass, you keep it. If it fails, you run it again. You drop that and you add that line, and you can feel like you've done as good a job as you possibly can. So everybody knows what I'm talking about when I talk about homogeneity of variances, right?
Can you explain
Again, this
that?
is Stat 101 kind of stuff. You were expected, you don't know?
No.
So the bottom line is this. You've got your four means, right? A, B, C, D. You have, and this is station. We have 4 cells.
Okay.
Each cell has 3 replicants, right? Each cell has a mean and a variance. And one of the things we worry about is what's the dependency of the mean on the variance. And one of the assumptions of all the multiple comparison tests is that the variance is the same in every cell. Now, my argument is, so what? We don't care because we're basing our test on this. We're not basing it on, you know, the mean and the variance of each cell. We're not basing it on those 4 numbers. We're basing it on this calculated in ANOVA. So that's why I've always felt like, I don't get this, why this is such a, why is this still a thing, as John Oliver would say. But again, just like the whole normality stuff, there are some people who go absolutely bananas over this issue. And again, if you really, it becomes a problem more when N is very different. Well, when I say N is very different, I'm not talking about you lost 1 rep. I'm talking about you got 3 in one, you got 3 reps in one cell, 10 in another, 15 in another, 20 in another one. When you're that unbalanced, all sorts of crazy things can happen. Why? Because the error bars, based on the cells, are going to be a function of n, right? So how do you calculate a t-value? Alpha at 95% times the variance divided by the mean divided by n. So when you're dividing by n, if you divide by 3 replicates, you're going to get a big number. If you divide by 30 replicates, you're going to get a small number. So it's because all these tests involve dividing by n, whether it's balanced or unbalanced is the really important thing. And the actual standard deviation value is not important at all, or variance value, because we really care about the population variance, not the variance in the cells. You know, that's why we do ANOVA, for God's sakes. Anyway, again, I tell you these things primarily for completeness and that you don't, I don't send you down the wrong road. Most of those tests are absolute crap. As I said, the only ones I truly believe in are the Tukey one and this one. Scheffé is also really good. Scheffé is probably actually the strongest of all the tests. The problem is it's incredibly conservative, meaning that it won't detect all your differences. It'll tell you everything's the same, even when they're not. So most people feel that Scheffé is a little bit too conservative, and you know, we want tests that will tell us they're different when they are. We don't want tests that will tell us they're not different when they are different. In contrast, all the other 10 tests are too liberal, meaning they find differences that probably aren't really there. And that's why most people don't use any of those tests. That's particularly true of all these multiple range tests. They're, most people don't like those things at all. Okay. So let's start looking at a few implementations here. Where's my mouse? Can't find my cursor.
It's on this screen, so if you add the split screen or
What the
this,
hell?
where it shows on this, before it shows your
How'd that
laptop.
happen?
You just hit escape.
Function
Yikes.
maybe.
It's extended desktop, so scroll
Why is
up to
that
the side.
happening?
Word view.
What the hell's going on here? I don't know how to get rid of this damn thing. How do I turn you off? Oh. Why did this happen? Oh. Found it. Okay. I'm still not on the screen. How do I get on the screen now? What is going on? What did I push? Oh, look at that. There we go. I somehow must have pushed one of my function keys. So let's go back to NAS1, which is a lousy example. because there are actually no differences amongst the means. Now recall we had this data set called NAS1 composite. And it has these 4 stations, 3 replicates in each stations. And so we can do a proc GLM data equals UD dot NAS1 composite and the classes station, there's just one class here, keep it simple. Tell you what, this is dumb. Let's do the thing that we really mean. Yeah, let's just keep doing what we're doing. And now we need a model statement. And I've already forgotten what's in this model. NAS1 composite, where are we? Okay, so the model is, we'll check out N, log N, and S, and that all equals station. And now we'll do our means test. And we're going to do it over the variable station. We tell it, we put a slash to say, here come the options. And then I'm going to use Tukey because that's Paul's favorite. I'm going to use lines. And I'm going to hit run. So let's go ahead and run that and see what happens. So the most, here it tells you we have 4 classes. And for the variable n, by the way, this first box is always model, and model will include all of the variables. There's only one here. And here's our mean square error. So this is, and then below it, you'll give us our R square coefficient variation root mean square, which is the square root of the mean square, right? So the mean square is an estimate of S squared. The root mean square is an estimate of the standard deviation. And I'm talking about the overall, the experiment-wise, not the one for every cell, right? And unfortunately, in this case, you can see there's no differences amongst the means. But when we log transform, whoops, what did I do? But when we log transform log in, we do find differences. As I recall, we've already convinced you that the log transform is the better value here. So now that we know the 4 stations are different, we want to know, and here's this pretty little station 0, station 10, station 100, and station 1000. We want to know which one of these are different. Just looking at those values. And by the way, these are the cell. This is a box plot. So what's the difference between the diamond and the line? One's the mean and one's is the mode and mean very close. And this one And I believe, which is which? I can't even remember. I have to go back and look at my lecture notes every time. Okay, but just looking at this, it certainly appears, but what we're looking at here is this. The mean and the mean and standard deviation for every single cell. That's what this is a plot of, okay? So is that a good, I mean, just looking at that, you can see that the station 1000 doesn't overlap with the other three, whereas the other three overlap. So I'm going to guess that when we're done, station 0, 10, and 100 are alike and 1000 is different. That's what I'm guessing. For richness, no difference. And sure enough, these things all overlap. So this is N. We're going to ignore this because it was, and sure enough, you see these? Here's your means for every cell. Whoops! Here's the means for every cell. Here's the number of replicates from each mean. And all these A's mean they're all the same. So let's go ahead and look at log N. And sure enough, it tells me a little bit of what I thought was true, meaning that it's saying station 10, 100, and 0 are the same, but it's also saying station 0 and 1000 are the same. So how do I present this in a paper? The way I would present this in a paper is I would go mean for station. And mean, yeah, I would do it, I'd probably do it the other way around. I'd put the word station on top. So you can do this in Excel, so these are separate sections. I go station 10, I'm going to leave the 0, and the mean is 3.2, and station 100, and the mean is 2.9, and station 0, and the mean is 2.7, and station 1000, and it is 1.3. Now this says these three are the same, so we draw a line like that. And this says these two are the same, so we draw another line like that. And so this is how, let's make some space. This is how you present the results of a multiple comparison test. And unfortunately, SAS doesn't put it in something that's easy to cut and paste right away. You actually could cut and paste those into Excel and use the, one column at a time transposing thing. Maybe it would save you some time. But then you can use the underlying functions for the squares to do that. So you could kind of do it either, if you make a table though, it makes this a little easier to do. We could also just do it as text by putting tabs between the stations and using the underlying function. Okay? So it's not too difficult to translate this into this format. So, who has never seen this format before? Is there someone who's never, really? Really? Oh my gosh! Again, that's like undergraduate statistics. You should have seen this somewhere before. The point is, this is a standard way to display a multiple comparison test. Got it? So this is a multiple comparison test looking at which means are different which of the treatment levels are different. And we, in your text, you say the line represents not significantly different at the P equals 0.05 level. Okay? So then you'd have this, and you'd write, so you'd have like table 1, means, station means, period, and then lines indicate, I can't spell, no significant difference at the 0.05 level. That's exactly how you would present this in a paper, okay? Now, let's say we could do more. It would be, let's say you don't believe this. Well, never mind. I'll save this for the next one. Let me not go down that road right now. Another thing you might want to do is back transform these abundances and present the back transformed values because it'll make more sense to people. So there's S. But again, S was not different anywhere, so it's no fun. So if we want to back transform those values, how do we do that? Well, we could do proc summary. I'm going to copy this. The easiest thing is to do it all in Excel, by the way. But I'll show you how to do it in SAS anyway. Right, because once you have this in Excel, you can apply the formula and back transform them. But we got to get the means first, so proc summary. Whoops. I'll use means instead of summary. We can use either one. We'll use summary. No, we gotta use means. Hopefully this data set is sorted. And the only one we care about is log n, so I'm just going to get log n out. Output out equals x, mean equals log n, std equals, I'll call it s, log n. And let's print it. Clock, print data equals x, run. So let's run this bit. I gotta look at my log window. This may not work if it's not sorted, I'm hoping it is. Whoops, hit the wrong button. I'm gonna right click, submit selection. Oh good, it worked. And what we get is, oh, we see we got this because I didn't use no print. So let's go back and fix this. So we get this table. So now I know the log. The log means are exactly what I got in my other test, right? You can see it here. Actually, this is 3.3. I didn't round off right the first time. So now we have a data set that looks like that. So let's put this up. So let's go back here. Let's go back and, well, I didn't really need to print that, I guess. Let's go back to my So now we have this data set like that, which is almost identical, which is identical essentially to this data set, except it doesn't have the lines, right? It's got the mean, the number, the name of the station, but it also has some other information because I put in it the standard deviation, and I put in, because I put in the standard deviation. So now what we want to do is back transform those. So we'll go to a data step, and I'll call it back set X. So the mean, right, the new mean equals log n equals exp log n minus 1. Now, why am I doing that? Recall that we used, ln was log n plus 1. So, to go back this way, we go e to the x. We implement e as the exp function. So I'll call it back is exp ln. Now we got to take away the 1, minus 1. Okay? Now can I do the same thing with the standard deviation? No. Recall that log scales are fat for the low numbers and skinny for the big numbers. So we got a first, so we don't do this and then plus or minus the back transform value. We do the subtraction first and then back transform. So our lower value is going to be exp log n minus s log n minus 1. And our upper, whoops, equals exp log n plus s log n. Again, minus 1. And so let's run that. And if we open up back, you'll notice two things. One is that, well, first we have our transform means, but you'll also notice that these lower and upper bounds are uneven. It's going to be shorter below the mean and higher above the mean. So if you're going to plot these things, I can't remember how to do that, so I won't show you that right now. But what we could do now with this information is I could build a new chart with the back transform means. So for 10, it is 25. For 100, it is 17. For 0, it's 14. And those are together. And finally, for 1,000, it's 2.7. We'll call it 3. Okay? So these are the back transform means. All right. We'll see you on Thursday. I will save this right now. I'll give it a little title.